Gas stoichiometry. This is nothing different than stoichiometry that we've always done, except in this case we're not going to be finding grams of something. We're generally going to be finding the volume of a gas or the moles of a gas or something like that. So all you got to remember is stoichiometry is a ratio of moles of substance. So if you need to find the moles, find the moles. Let's go through the first problem. We're going to start with one that's fairly simple, and then we'll do one other one that is a little more difficult. How many liters of carbon dioxide gas will be theoretically produced in the combustion of 32.0 grams of methane, which is CH4, that is combusted at STP? Remember, that's standard temperature and pressure. Methane has a molar mass of 16 grams per mole. So the first thing I look at is the equation is given to us, and it is balanced, which is important, of course, in stoichiometry. The first thing we want to do is we want to find those moles of methane, because we have 32 grams of methane with a molar mass of 16. We take the mass of methane divided by its molar mass, and we get 2.00 moles of methane. Now, looking at the stoichiometric ratio of methane to carbon dioxide, since that's what we're trying to find, it is a 1-to-1 ratio. So if we have 2.00 moles of methane, we should theoretically produce 2.00 moles of carbon dioxide. Now, since this is at STP, and we all remember that STP, standard temperature and pressure, that 1 mole of any substance, any gas, if you will take up 22.4 liters of volume. Well, we have 2 moles of gas. So if we take the 2.00 moles of carbon dioxide and multiply it by that 22.4 liters per mole, we'll get 44.8 liters of carbon dioxide that should theoretically be produced. Notice we were able to multiply by 22.4 because it was at STP. If it's not at STP, you're going to have to use the PV equals nRT problem. Let's see an example of that right now. How many milliliters of oxygen gas will react with 5.00 grams of magnesium when burned in air at 20 degrees Celsius and 1 atmosphere of pressure? So you'll see we are at standard pressure, but we're not at standard temperature. Standard temperature would be 0 degrees Celsius or 273 Kelvin. So the first thing we're going to do is write down the equation. Magnesium reacts with oxygen to produce magnesium oxide. Then we must balance the equation. 2 magnesiums react with 1 oxygen molecule to produce 2 compounds of magnesium oxide. So what's the next step? We know the amount of magnesium we have, but we want to find out the milliliters of oxygen gas that are going to react. So what I'm going to do first is I'm going to find my moles of magnesium. And I'm going to take the grams of magnesium and divide it by the molar mass of magnesium, which is 24 grams per mole, and I'm going to get 0.21 moles of magnesium. So I write that underneath the magnesium. If you look at the stoichiometric ratio of magnesium to oxygen, you'll see that it is a 1-to-2 ratio. So we need half as many moles of oxygen as we need magnesium, which gives us about 0.11 with 2 sig figs. So now that I know I have 0.11 moles of oxygen, I can find out the milliliters of oxygen gas using the equation PV equals nRT. Notice we can't just take the moles and multiply by 22.4 because it's not at STP. So let's go through and plug in our values for the PV equals nRT equation. The pressure is 1 atmosphere. The volume is what we're going to try to find. Remember, as we solve for volume in this case, it's going to be in liters. The moles of O2 that we have is 0.11 moles. Notice I used the R value of 0.0821 because my pressure is in atmospheres. And of course, my temperature has to be in Kelvin, so I take the 20 degrees Celsius and add 273. When I solve for this, my volume is 2.6 liters. Notice it's in liters, so in order to convert that into milliliters, I multiply it by 1,000, and I get 2,600 milliliters of volume. So to react with 5 grams of magnesium, it would take up 2,600 milliliters of oxygen gas to react.